Another phenomenon that contradicts the classical theory is the photoelectric effect. In this experiment, a metal surface is struck by light, and this light will cause the ejection of the electrons from this negative metal, and they move towards the positive electrode, the anode. And subsequently, a current will flow through this circuit. And this light, it has a given energy or a given frequency that we call the threshold frequency. So below this threshold frequency, no current could be observed. So the photoelectric effect cannot be observed if the light has a frequency less than this threshold frequency. Also, some of the important observations made from this photoelectric effect is that if the energy of light is increased, therefore the kinetic energy of the ejected electrons increases too. And also, if the intensity of the light is increased, here we can notice that the current or the photocurrent also increases. And this went against the old theory from the electromagnetism principles, because according to this old theory, even a very low energy, which means an energy that has a frequency below this threshold frequency, will result by the photoelectric effect, will result by the flowing of current. And also in this old theory, it says that if the energy of the light is increased, so the current will increase too. And this was not the case, because the observations from the photoelectric effect went against this old theory. So we have here another puzzle to solve. And in 1905, Albert Einstein used the quantum theory postulated by Max Planck. So what Einstein suggested is that this electromagnetic radiation from the light behaved like a stream of particles. So if the intensity of this electromagnetic radiation is increased, so the number of these particles will increase too. So the number of particles will increase. And if this number increases, so the current will increase, because we'll have more electrons that will be removed. So he did explain this observation. And also, by increasing the energy of the light, it means that the energy of this particle will increase. So each particle will have an energy that is increased, and therefore the kinetic energy of the removed electron will increase, because we had a transfer of energy between the photon and the electron. So the two observations were explained. So this puzzle was solved using this suggestion that light behaved like a stream of particles, and each particle, it has a name, which is photon. And a photon, it has an energy to a quantum which is equal to h nu. And here we have another example how the quantum theory could be applied to resolve problems at the atomic scale. Let's do the example 2. Here we are asked to calculate in joules the energy of this photon with this wavelength and a second photon with this wavelength. So we have two different wavelengths, which means that we have two different energies. Let's calculate the first one, the A. So we apply the expression of E equal to h times nu. Here the h is the Planck's constant, and here we have the frequency of light. So this relationship that represents, here we have the Planck's constant, and here the frequency of light, or of the electromagnetic radiation. and also it is equal to h times c over lambda. So we replace by their values. So we have the Planck's constant equals to 6.63 times 10 to the negative 34 joule second times the speed of light in meter second negative 1 over the wavelength, the given wavelength, which is equal to 3.80 times 10 to 4 nanometers. But here we have in nanometers, so we cannot make the calculation, so we have to convert to the meter. We know that 1 nanometer is equal to 10 to the negative 9 meters. So we can cancel each unit second with second. At the end we get a result in joule. So the energy of the first photon is equal to 5.23 times 10 to the negative 21 joule. And the same method is applied for the second photon, and we find a value of 5.23 times 10 to the negative 15 joule. Here we can notice that the energy of the first photon is smaller than the energy of the second photon. So here we have a more energetic photon, this second photon, the B. And also, in which electromagnetic region these photons are found. The first one we can see from the wavelength. Here it has a magnitude of 10,000, which belongs to the infrared region. And here it is in the region of the X-ray, because we have a magnitude of 0.01. So here the first one we have the infrared region, and the second one is the X-rays. Now let's talk about the process of how the electrons are removed from the metal surface. Here we have a photon of energy h nu that strikes this metal surface. After that, an electron is ejected from this surface. So here we have the electrons that are bound to the electron surface by an energy that we call W, or this, it is also called the work function. So this work function is the energy binding of the electrons to the surface. So if the energy of a photon, which is called E, is at least equal to this energy, so here we can have an electron that will be dislodged from this metal surface. Now, if the energy is higher enough, or if higher enough of the work function, so the electrons will be released from this plate, and also the excess of this energy will be converted to the kinetic energy. And we can summarize this phenomenon as this expression. So the energy of the photon that strikes the metal surface is equal to the binding energy of the electrons to the metal surface plus the kinetic energy. And this work function is also called the energy, the threshold energy. We can call it the threshold energy, because it has a value of h times threshold frequency. So here we have the threshold frequency. And the kinetic energy of this ejected electron is equal to the energy of the photon minus the work function. And we can write it like this: h nu, the energy of one photon, minus the threshold energy, which is equal to h times nu 0, and it is equal to h times nu minus nu 0. Let's do this example. So the energy that holds electrons on a magnesium metal is equal to 5.86 times 10 to the negative 19 joule. Here we are asked to calculate the minimum frequency of light required to release electrons from the metal in joule and in electron volt. So we have here the energy that holds electron on a magnesium metal. The energy that holds the electrons to a metal surface is called a work function. So we can write that the work function is equal to this energy, joule, and is equal also to H nu 0. It is the threshold frequency. We are asked to calculate the minimum frequency of light required to release electrons from the metal. So the minimum energy or the minimum frequency that is required to release these electrons is called the threshold frequency, which is. So here the threshold frequency is equal to nu 0, the work function, divided by the Planck's constant, which is equal to 5.86 times 10 to minus 19 joule divided by the Planck constant, joule second. So here we can see that the joules units are cancelled, and at the end we get a result in second, the negative one, or in hertz. By making the calculation, we get a value of 8.84 times 10 to the positive 14. So here we can say it is the threshold frequency. In second, negative 1, or in hertz, the same thing. Now, for the second question, what is the kinetic energy of the ejected electron if light of frequency 2 times 10 to the 15 hertz is used for irradiating this metal? So here we are using a second frequency, a different one. Let's call it 2, that is greater than the threshold frequency. So because the kinetic energy of the ejected electrons is proportional to the energy, it is also proportional to the frequency. So here we can expect that the kinetic energy will increase. So what would be the kinetic energy in this case? So here we have the relationship that relates the energy of a photon, which is equal to the binding energy or the threshold energy plus the kinetic energy. So here the kinetic energy is equal to the energy of the photon minus the binding energy. And this energy, it is said that it has a greater frequency, which is equal to h times the frequency 2 minus the work function. So we have only to calculate this part, which is equal to the Planck's constant and here we have this frequency, 2 times 10 to plus 15 second minus 1 minus the binding energy, which is equal to 5.86 times 10 to the negative 19 joule. So we can see here that we'll get a value in joule. So the kinetic energy in this case is obtained from this calculation, which is equal to 7.40 times 10 to the negative 19 joule. So here we can see that the kinetic energy is less than the total energy, which is equal to this. We can calculate this energy of the photon. Here we have the energy of a photon, which must be greater than the kinetic energy. So we can calculate this value times 10 to the negative 18 joule. So we can see that here it is verified that the kinetic energy is less than the energy of a photon. Now let's talk about the stopping potential. The stopping potential is applied in order to prevent the ejection of the electrons from the metal. And we apply this potential that we call dropping potential. So how does it work? We have seen that in order to eject electrons from the metal, we have to provide an energy of a given frequency. So we have seen that in order to prevent the ejection from the electron from the metal surface, we have to provide an energy of a given frequency that we call threshold frequency. And this energy must be equal to the work function. And when the electrons are ejected, we have the current that flows through the circuit. So the electrons that are ejected, they have kinetic energy. So the energy that is provided is divided between the work function and the kinetic energy. And in order to stop this photoemission and to stop also the photocurrent, so in order to stop this ejection of the electron, we have to add an energy to the work function. This energy is added as electrical energy, that is the charge or the elementary charge times the dropping potential. And here we have an energy. If we add this energy to the work function, it will be equal at least to this provided energy. So we can write it like this, is equal to E minus the work function, and here we have the expression of the kinetic energy. So the applied dropping potential must be at least equal to the kinetic energy in order to stop the ejection of the electron and to stop the current through the circuit. Let's do this example. So first question, when this wavelength from light is used in an experiment with a metal, the measured photocurrent drops to 0 at potential minus 0.8 volt. We are asked to determine the work function of the metal and its threshold frequency. So in this example, we have a metal that ejects electron after receiving this energy with wavelength of 180 nanometers. So here the energy that is provided is equal to h nu, which is equal to hc over lambda. This wavelength is equal to 180 nanometer. It is the total energy, and this total energy is equal to the work function plus the kinetic energy. Here in this question, we have applied a dropping potential that is equal to minus 0.8. We are asked to determine the work function. So the question is to determine the work function. The energy that is applied is obtained from this relation. So we have this value. And in order to stop this photocurrent, we have to apply an electrical energy that is equal to the kinetic energy. with the charge Q is equal to minus E, which is the elementary charge. So we have the kinetic energy that is equal to 0.80 volt, electron volt. Now we can calculate the work function that is equal to the total energy minus this kinetic energy. Here we have the kinetic energy in electron volt. So we have to calculate the energy in electron volt. We just replace by the value. We have h, which is equal to, we have here the Planck's constant times the speed of light, 6.63 times 10 minus 34 joule second, times, here we have the speed of light, the applied wavelength of the light is equal to 180 nanometers. We have to convert to meter. 1 nanometer is equal to 10 to the negative 9 meter. So we can see that we have cancelled all this unit. So here minus 1. We have at the end a unit in joule. And because here we are asked after that to determine the frequency of the threshold frequency, so it's better to let this part in joule and to convert the kinetic energy to the joule. So minus, here the kinetic energy was found 0.8 electron volt. So it will be 0 electron volt times, we know that 1 electron volt is equal to 1.6 times 10 to the negative 19 joule. And here the value of the work function in joule is equal to 9.77 times 10 to the negative 19 joule. Its equivalent in electron volt is equal to 6.11 electron volt. Now we are asked to determine the threshold frequency. From the work function we can get the threshold frequency or the threshold wavelength. And the threshold frequency is equal to the work function divided by the Planck's constant, which is equal to the value of the work function in joule and the Planck's constant in joule also second. So that's why we have calculated the work function in joule. It's better to avoid to convert here. And we get a threshold frequency equals to 1.47 times 10 to the positive 15 Hertz. Second question. In this work we have a yellow light with this wavelength, which is incident on a surface whose work function is equal to 1.20 eV. What is the stopping potential and what is the cutoff wavelength? The cutoff wavelength, which it means the threshold wavelength. So we have here, for this example, a metal surface that is irradiated by an energy of wavelength which is equal to 589 nanometers. We have electrons that will be ejected, and we have the work function that is equal to 1.20 electron volt. Here the work function, which means the binding energy, is equal to 1.20 eV. First question, what is the stopping potential? Which means that if we want to stop the electron ejection from this plate, what would be the value of the tropic potential. So we know that the electrons are prevented from leaving the plate when we apply an electrical energy that is equal to the, at least equal to the kinetic energy. So here we have to calculate the kinetic energy, and the kinetic energy is equal to the, here we have the energy that is provided. So it will be equal to the total energy that is provided to eject this electron minus the work function. So we have just to replace, here we have this, here we have the work function in electron volt, and here it will be in joule. But we can convert this energy to electron volt, or we can convert this to the joule. But it's better to calculate this in electron volt. So we have here the energy that is equal to H times C over the wavelength minus the work function, which is given. Here we have to replace and here we have the wavelength, which is equal to 589 nanometers times, we have to convert nanometers to meters. Now we have to cancel all this unit, meter with meter. We have the joule, and we convert the joule unit to the electron volt. So we know that 1 eV is equal to 1.6 times 10 to the negative 19 joule. So we have cancelled the joule. At the end we have this part in EV minus the work function is equal to 1.20 electron volt, 1.20 eV, and we get a value here. The kinetic energy will be equal to 0.91 eV, and the tropic potential is obtained from this, because we have said it is equal to kinetic energy. So the tropic potential will be equal to minus 0.91 volt. Here is the tropic potential. Here, don't forget that the charge is equal to minus E. And the last question, what is the cutoff wavelength? Here, from the binding energy, the work function is equal to H times the threshold frequency, which is equal to H times C over the threshold frequency, or the threshold wavelength. And the threshold wavelength is equal to H times C over the work function. So here we have to be careful about the unit. Here it is in joule second, here in meter second to the negative 1, and here it's better to convert the work function to joule, so we can get the wavelength in meter. Here the joule is, the work function is equal to 1.20 eV, so we have to convert to the joule. 1 eV is equal to 1.6 times 10 to the negative 19 joule. And at the end we get the wavelength, the threshold wavelength, which is equal to 1.03 times 10 to the negative 6 meters, and in nanometers it gives about 1.1036 nanometers. So here is the threshold wavelength. To summarize, understanding the electronic structure of atoms requires an understanding of the properties of waves and the electromagnetic radiation. And also, the electromagnetic radiation includes the radio waves, microwaves, visible X-rays, and gamma rays. Planck postulated that the energy is quantized. Also, Einstein followed the works of Planck and postulated also that photons are particles of light and they have energy that is quantized. And we have seen also that ejection of electrons is or can be prevented by applying a dropping potential.